Thanks for having me here today. I'm going to talk to you a little bit about Minnesota's experience with PFAS, what's going on around the country, and then how are people responding to this problem. If you looked at the caricature, the picture that they have out front on the easel, which was a total surprise, by the way, kind of cool. The quote they gave me was, "PFAS are scary," which isn't exactly the public health message we're trying to deliver. But it is the message that the public has taken away from PFAS, which is, part of the problem with emergent contaminants is often the public message gets away from us before we have time to help explain to the public exactly what is going on, and it doesn't help that we're learning as we go, which makes it hard for the public necessarily to trust what we're telling them. Because things are evolving so quickly. So I want to also talk a little bit about why, yes, some PFAS actually are kind of scary, but not all of them. And part of our job is going to be helping the public understand that part of the message and also helping them to understand that there are big differences between PFAS and there are big differences between some exposures and others. So let's jump right into it. We're going to talk about what are PFAS and where do they come from. I apologize if this is old news for all of you. I never know with an audience, especially kind of a mixed audience, so I'm going to do a little quick background. How do they behave in the environment? What are some of the health risks that may be linked to PFAS? And then what are the drinking water values that are evolving and going nuts all over the country? And then what do we do when we find PFAS in drinking water wells? So very quickly, per and polyfluoroalkyl substances. We used to be able to use a very simple name of PFC, now it's PFAS, because we've come to recognize that we're really talking about a much larger class of chemicals. Unfortunately, somewhere over 4,000 of these things have been synthesized, potentially manufactured, and maybe out in the environment. And we've only started to wrap our heads around maybe 25 of them. So that's pretty daunting. So yeah, that kind of falls in that class of that could be scary. But we don't know that most of these are actually out in the environment, and we don't know that any of them beyond the ones we've already looked at even pose any health risk. So we're hoping to maybe get a little more of a handle on that as the years go by, but right now we're going to be focusing on the ones that we have some understanding of. These have been used since the 1940s when they were actually first synthesized in the late 30s in research labs, and then they went into production in the 1940s. Their production exploded starting in the 60s with the advent of Teflon and into the 70s. And you can see some of the many uses because they are stain-resistant, grease-resistant, water-resistant, and also thermally resistant. They have a lot of useful applications in a host of various products, and you can see some of them here. Starting in 2002, 3M voluntarily began to phase out production of PFOS and its related chemistries. Very quickly, EPA also went forward with a voluntary phase-out program with the major manufacturers of PFOA. These are the two everyone's heard of, right? PFOS related to Scotchgard and those kinds of things. PFOA related to Teflon and Gore-Tex and that sort of thing. So these actually have been phased out of use in the United States, except for a few important exceptions. Firefighting foams that contain these chemicals, if somebody had an existing stockpile, they are still allowed to use those foams. Some states are starting to say, let's rethink that plan. And frankly, the military has already said, yeah, we're out of the 8-carbon foam usage business. We just don't want to be using that anymore, and they've shifted to a different chemistry that we hope will be less environmentally and human health risk. But there are still approved uses for PFOS in chrome plating or other metal plating because it's used on the vats as it's a surfactant, so it forms a film on the vats that suppresses the production of mist. Because if you've seen Erin Brockovich, you know that breathing chrome-6 is a bad thing. And so this is a worker safety thing. They are looking for alternatives. But some facilities are still allowed to use this, and there are still a few other smaller applications where these chemicals are used. Phasing them out in the US, Canada, Western Europe, Japan, Australia, that does not mean they're gone. Production shifted to Southeast Asia and Eastern Europe, and so they are still produced, not at the same volumes, it appears. So in the Western world, we're seeing declining concentrations in the environment, but we still see the release of them in those parts of the world, and so in the Western Pacific, we still see in some animals rising levels of PFOS in their bodies. So what are the major sources? You get a little indication from that last image, but so far what we've identified as the most significant sources is first firefighting and fire training sites, because that's a place where we took PFAS bearing foam and deliberately released it to the environment. That's how you use the foams. Unfortunately, some of these chemicals are so soluble and so mobile in the environment that they simply either quickly infiltrated or they rapidly ran off to surface waters, left these sites and went all over the place. And so we also know about this because the Department of Defense has done a massive project over the last few years of identifying these locations and starting investigations. And so they've already identified over 400 potential sites around the country. So that was one of the first places where they were identified. Also industrial sites. And a lot of people think, oh, we're talking about the place where they made these chemicals, but we're not. We're talking about both the primary production and the secondary manufacturing, so places where they used the chemicals to create some of those products that we were just looking at. So we're talking about chemical plants, plating and etching facilities, paper, textile, and leather coating facilities. Michigan's biggest site right now is a Wolverine boot manufacturer who was coating the leather with a water-resistant coating that got away from the plant into a lake. The concentrations were high enough that there is PFAS foam on the beaches where the waves come in on this lake, and the water gets aerated, and they've got high concentrated foam that kids were playing with and spreading all over themselves. And the little ones, of course, little kids, put stuff in their mouths. So yeah, this is why the public finds this stuff scary. The semiconductor industry, photo and lithographic industry. One of the big sites in Vermont was, and also in Vermont, it was a wire coating facility where they were putting PFAS-bearing coatings on the outside of wires because of the thermal resistance. Hoosick Falls, that was a fluoropolymer production plant that they were using PFOA and they had emissions into the air. So secondary manufacturing is actually a big deal. So when people started looking at the initial sites where these were being found, 3M and DuPont plants where they were making the chemicals or making Teflon, a lot of the country said, well, we don't have DuPont or 3M in our backyard, so not our problem. We're quickly learning that that's not true. And then there are the places where we aggregate all the wastes of society, all the chemicals of society, so our landfills and our wastewater treatment plants. Now, the concentrations in those areas vary significantly, but when we sample at landfills, as we've done in Minnesota, we find them in every single landfill at some concentration, and especially concentrated in the leachate. What happens to that leachate? Well, a lot of times we gather it up because we don't want it infiltrating to the groundwater, and we ship it to the wastewater treatment plants. Wastewater treatment plants were not designed to remove PFAS. Some of the advanced cleanup technologies at wastewater treatment plants may reduce the concentrations. Some of the processes actually convert what we call precursor compounds into the PFOA, PFOS that we're also concerned about. So sending it to a wastewater treatment plant is not the solution, because what largely happens is the water-soluble PFAS end up going out to the receiving waters of those systems. And the less soluble, more readily absorbed to carbon forms end up on the biosolids. And sometimes those go right back to the landfills and were put on as cover. So we've got this, you'd like to think it's a closed loop, but it's really not. It's a leaky loop. The other thing we do with a lot of our biosolids is spread them on our agricultural fields to amend the soil. And we've already heard of 2 places, one in New Mexico, one in Maine, where it was spread on fields where dairy cattle are grazing. The cattle were contaminated, their milk was contaminated, and rightly or wrongly, there's a lot of debate about it, but those farmers had to destroy their herds. And so it's become a big concern about the many, many ways this stuff can find its way into our food supply. But because these chemicals are so resistant to any degradation, and because a lot of them are very soluble, and because some of the precursor compounds I briefly mentioned are volatile, these things have become spread globally. They've been PFOS, PFOA, and some of what we call terminal PFAS, like those 2 chemicals, have been found worldwide. They're in all environmental media. They've been found in the soil of Antarctica. They were even tested for in penguin poop in Antarctica. So it's everywhere. The thing that really triggered a lot of the investigations was in the late 90s when researchers started finding these chemicals in Arctic species. They're also found in human blood, and that's what really triggered EPA's decision to start phasing them out. We find some of these chemicals, PFOA, PFOS, PFHXS, and PFNA, pretty much in the blood of every person in the Western world. Just about 99 point whatever % of people tested. So it's a real concern, and because of that atmospheric distribution, it looks like pretty much global distribution of these things. It wasn't, however, until about 2015 that the country really became aware that this was a widespread problem. And that's because of a program that EPA uses to look for unregulated contaminants that may be in the environment and potentially could get into our drinking water. And so every 5 years, they test all systems over 10,000, that serve over 10,000 people, as well as some randomly selected smaller systems. And in 2013 to 2015, they put 6 of the PFAS compounds on their list to be tested. Now, they weren't found in a ton of systems, but in 4% of systems, they had detections, and 1.3% of those systems had exceedances of the EPA's newly released lifetime health advisories of 70 nanograms per liter for PFOA and PFOS combined. So that is a significant chunk of the American population, not maybe a large percentage, but we're talking about the drinking water of about 6 million people. And there are some caveats around those numbers. First of all, the list that they used did not include the most soluble and some of the most widespread of the PFAS compounds. So PFBA, PFPEA, those 2 are the most water soluble. So they're the most likely to be found. So we didn't test for those. They're hard to test for under the EPA's method. The other thing is they have had relatively high reporting levels on the testing that they were doing. And so Eurofins Analytical revisited the data from the UCMR3 testing, looked at data that they already had for a lot of those systems, did sort of an analysis, and they projected that actually there were potentially much higher numbers of systems that would have been identified at least as having detections had we had lower reporting limits than were used. The reason for that higher reporting limit was because they wanted a lot of labs to be able to do the testing and be able to meet the requirements of their method. The other caveat is they were testing the finished water of those systems. So we had an example in Minnesota. You'll see a dot in northern Minnesota that's red. That's Bemidji. That's their city water system. Their first round of testing, because they do 2 rounds, the first round of testing was fine. The second round of testing exceeded the lifetime health advisories. And the reason is they were pumping different wells. And 2 of their wells are highly contaminated, and 3 of them are less contaminated, or the day that they tested, they managed to hit it when they were pumping the 2 that have no PFAS in them. So there's a lot of caveats around this. It's a good data set. It helped to raise public awareness, but we need to take it with a little bit of a grain of salt. I've already thrown a lot of acronyms at you. I already scared you with 4,000 plus chemicals. So let's get our arms around this a little bit, and let's talk a little bit. I promise I'm a geologist, so the chemistry is not going to be scary, but we probably have to understand a little chemistry before we can talk intelligently about these chemicals. So here's the family of PFAS, and it involves both non-polymer and polymer chemicals. And we can pretty much set the polymers aside. These are largely inert and not bioavailable. So when they get in the environment, they don't degrade. They generally are not something that you take up. Teflon, which most of the public thinks is their biggest, scariest exposure route, falls under the polymer side of this family. And yes, there's a little bit of PFOA that remains in the Teflon when you manufacture it and you put it as coatings on things. But that is not the major exposure route that most people have. Yet, because of the DuPont site, it was a Teflon manufacturing facility, that's what's stuck in people's heads. So they say PFOA they equate it with Teflon. On the non-polymer side, that's where we're most concerned, and there are 2 major classes. The perfluorinated, meaning the carbon chain that makes up the backbone of these chemicals is fully fluorinated, and polyfluorinated, meaning that carbon chain is mostly fluorinated, but there's at least 1 or more carbon in that chain that has something else attached to it, usually either hydrogen or oxygen, and that's a weak link, and it makes them degradable. So we're mostly concerned under the perfluorinated side, and we're mostly concerned about what we call perfluoroalkyl acids, so another acronym, PFAAs. Those are what we also call terminal PFAS. These are the ones that will not break down in the environment. That short carbon fluorine bond there's nothing in the natural environment that will break it. But unlike a lot of chemicals we're used to, they're also soluble. So here's why we're so concerned. On the other side of this family, the polyfluorinated and a small subset of some polymers possibly may be what we call precursors, those chemicals that can degrade and form those terminal PFAS. So we have to know that those chemicals are there, that they're part of this big family. They're probably some of them are at our sites, but they're not the ones necessarily that we're concerned about in terms of human health risk, except that if we ingest them, we can metabolize them and then form them into PFOA. And that's exactly what happened with the microwave popcorn story. When they tested microwave popcorn and the popcorn bags, they didn't find PFOA, and yet people who ate more microwave popcorn had higher levels of PFOA in their bodies. Why? Because the precursor compound was what was in the bag and was getting on the popcorn, and people were eating it and metabolizing it to PFOA. So we have to be very cognizant of these chemicals, but right now we don't have good ways to test for them, so we're still at an early stage with them. I mentioned already that chemical structure. Long chain of carbon, anywhere from 3 to 20 or more carbons, fully fluorinated. And then the only other difference is what's attached to that chain for the PFAAs. It's either going to be a sulfonate or a sulfonic acid or a carboxylate, a carboxylic acid. Pretty basic chemistry. But the important thing is if you look at that molecular cartoon, that gives you a good idea. You can't see the carbon molecules because the fluorine huddles very closely around the carbon and doesn't allow anything to interact with the carbon, and that's why they won't break down. The naming often is very hard for people to get a hold of because there's so many of these acronyms and names and everyone gets confused. It's actually a simple system and you already know it whether you know it or not because it's the same as hydrocarbon naming. So as children of the industrial age, we already know these. Butane means 4, pentane means 5, hexane means 6, heptane means 7, octane means 8, on and on and on. And then you just slip in a PF in front of that, perfluoro, whatever the chain length is, and then that functional group at the end. So our example here is an 8-carbon chain, fully fluorinated. That means it's a PFO. It's got a sulfonate on the end, perfluorooctane sulfonate. And so you can build up a table of all of these things very easily based on just chain length, functional group, and that perfluoro prefix. But already we've complicated it. God bless our chemists, because for every single one of those, there's 2 different names, and your lab may use either one. People may use them interchangeably. So what is really going on? Well, these chemicals in their purest form are acids. They're very strong acids. So the minute they're released to the natural environment, they lose their hydrogen, they become an anion, a negatively charged compound. So when they're first formed, it may be perfluorosulfonic acid, but as soon as it's released to the environment, it becomes perfluorooctanoate, or octane sulfonate, excuse me. So whatever your lab calls it, what they're testing for is that anion, because that's what you will find in the environment everywhere except at pH 3, which you don't find very often unless you're looking for PFAS at Yellowstone. So disregard the fact that there are different chemical names associated with these acronyms. Just know that you're looking at that negatively charged one, but be sure if you're looking up physical properties that you're using the right CAS number, because the acid and the anion behave very differently, have very different chemical properties. So you need to be sure that you're talking about the right CAS number. All right, I already talked about the short carbon-fluorine bond, strongest bond in that we know of in organic chemistry. Takes a lot of energy to destroy that bond. So really right now, our main destructive technologies involve high temperature or high pressure. So mostly incineration, but there's some work on ultrasonic destruction and using cavitation and plasma technology. So that's kind of out there, Star Trekian sort of stuff that's being developed now. But right now, burning the stuff is basically what we've got. These chemicals are very soluble, and that's what makes them unique for persistent organic chemicals, because normally persistent chemicals like PCBs, dioxin, they get into the environment, they attach to carbon right away, and they don't go very far. These guys are very mobile, or soluble, they're very mobile, and that's why they're a potential concern for our drinking water. But there are some things we can say about predicting where they're going to be in the environment, because there are some general rules of thumb. The longer the chain of carbons, and the ones that have sulfonates attached generally are going to be less soluble, more likely to sorb to organic carbon in the environment. And vice versa. The shorter the chain, or the ones that have carboxylates, they're going to generally be more water soluble. And the bioaccumulation is similar. Longer chain and sulfonic or sulfonate compounds tend to bioaccumulate more, but it's complicated by the fact that even though they're water soluble, the main thing they like to do is attach to protein, which is unusual, and we don't have good models yet for predicting all of that. So even though PFHXS, the 6-carbon sulfonate, has a shorter chain, it's more bioaccumulative than PFOS, the 8-carbon chain, and we don't really understand why. But this allows us to do a little bit of general predicting about how these will partition in the environment. Carboxylates and shorter chain chemicals tend to show up in our waters, surface water, groundwater, while the sulfonates and the longer chains tend to be retarded back at the site or shortly down gradient of it. And so we can see that when we look at our sites. And similarly, in animals, we tend to see the sulfonates and the longer chain, but in plants, we tend to see the carboxylates and the shorter chain ones because they're mostly taking up water. So it helps us start putting these things into kind of little categories out in the environment and know what to be concerned about. And you can see this a little bit from what we've found out in Minnesota. This is a map of our PFBA plume, and you can see a very widespread area of contamination. That is over 150 square miles of contaminated groundwater, because that is the shortest chain, most soluble, and most mobile of the PFAS that we find at our sites. It follows where the water goes. So wherever water went, that's where the PFAS went, including surface water that is intimately connected to groundwater, and I'll show you that in a second. So this is a somewhat complicated thing, but unlike what a lot of people tell you, that these things don't follow the laws of man or science or God, they actually do. I mean, they're just going where the water goes. So we have to be on our game as hydrogeologists in understanding some of the really small details of what the groundwater is doing. You can see how those major faults that show in red seem to be controlling where we find PFBA and where we don't. The groundwater divide has played a big role. That dark shading that's below the colored shading, those are buried bedrock valleys, and you can see some alignment along those buried bedrock valleys. One of the major things we've seen that's controlling some of this widespread distribution has been groundwater surface water interactions. And that's something that we as hydrogeologists have not paid a ton of attention to on a lot of our sites, because usually our chemicals get into a surface water and pretty quick the bugs and the oxygen and the sunlight are breaking them down, or they're attaching to sediments. When we look at PFOS and PFOA at that area, you can see much smaller areas of contamination because they're longer chain, they don't go as far, although these are still huge plumes by anyone's standard. You know, you can't see the scale necessarily, but the plume on the left in Oakdale, Minnesota is 10 miles long. So we're talking about big areas. And you'll notice they're scattered all over the place in a pretty crazy LSD-induced trip kind of way that really had us freaking out, because when we started in 2003, we didn't have a lot of fate and transport knowledge, and we thought, these things are Frankensteins. We can't even predict where we're gonna find them. They're just popping up everywhere, willy-nilly. Well, what we found out was the reason for that was because we had a surface water system that had been highly manipulated by a watershed district, fully unaware of the fact that these chemicals were in the water, so it's not their fault. But that moved the stuff across a groundwater divide, and everywhere that it entered that, or followed that drainage system, which the surface water shown with the blue arrows, everywhere it entered that surface water system, if that surface water system was infiltrating, and throughout much of the course of this system, it's a losing system, so it is infiltrating, we were creating discrete little PFAS plumes. So we've got one out in West Lakeland Township that basically is starting or sourced out of a lake that all of this stuff was draining into, and then into some stormwater ponds that are, sadly enough, basically on top of a karsted limestone dolomite formation with sinkholes. But at any rate, the stuff is just dropping right down into these drinking water aquifers and creating discrete PFAS plumes miles from their original source. That plume on the right side of the screen for you, oh, it's the right side for me too, never mind. That's 6 miles from its source back in Oakdale, because all the PFOS that's out into the groundwater is primarily coming from the Oakdale site. So that's a fairly scary concept, that you can be creating isolated, discrete plumes in the groundwater miles from your source area. So what are the human health effects of PFAS and PFOA? Well, we have possible links, but they're supported somewhat by largely by animal studies, because we see similar effects in controlled lab animal studies. But these possible links are from correlation studies of human populations where they've had high levels of exposure, or comparison of high and low people who have higher or lower levels. Now, this is confounded by a lot of stuff, so we're still fighting it out. The toxicologists have a lot of disagreement about whether these are real or not. But you'll notice PFOA only has a link to cancer, and only two kinds, testicular and kidney. Cancer, and that's primarily been seen in the workers with really high levels of exposure. Cancer is not the driver here. It is the immune system effects and also developmental effects that are really driving this. And the reason, and we'll get into that in just a second, but understanding risk is really important. It involves exposure and hazard. If something is hazardous but you're not exposed to it, you don't have a risk. And this is what sometimes the public doesn't really understand. But for these chemicals, the major pathways of exposure for the general population appear to be our diet, and we don't quite know why or where it's all coming from. Is it uptake into plants and animals, or is it primarily from our food packaging? And as we move PFOA and PFOS out of our food packaging, are we less exposed? But also drinking water and incidental dust and soil ingestion. And a study out of Canada and also the Netherlands showed that if you have carpeting in your house, you will predictably have higher levels of these chemicals in your body than if you don't. And that was because of the coatings that were put on almost all carpets and textiles for furniture throughout the 80s and 90s. But for people who are near contaminated sites, the primary exposure pathway is their drinking water, their fish and seafood that are in the surface waters near there, and then potentially inhalation if you're at a plant that has airborne emissions. So I'm going to move along quickly. The result of our not fully understanding the toxicology and some of the concerns about these developmental and immune system effects that are very subtle but are triggered during pregnancy and shortly after the baby is born has led to lifetime health advisories of 70 nanograms per liter on the part of the EPA, but then a host of different numbers across the country. Some as low as those in New Jersey of 13 and 14 parts per trillion for PFOA and PFOS. Minnesota has very low numbers. Some other states as well across the country have gone to 20 nanograms per liter. Why is that? It's because these chemicals are so highly bioaccumulative, because babies have a higher intake rate than adults for the water, and because we see biological response at extremely low levels that appears to trigger developmental effects in babies, low birth weight, low head circumference, and also suppressed immune systems. And that occurs at very low drinking water concentrations for the mother if she's exposed for a long time, and then passes it on to her baby during pregnancy and breastfeeding. And it's that breastfed infant born to a highly exposed mother that we're trying to protect for. Some states have numbers for other chemicals, and you can see a few of them on this map. Some, like Minnesota, Vermont, Massachusetts, Alaska, have also done some form of additivity, either a straight additivity or Minnesota, always got to be different. We do a kind of a TEQ-like approach where we do a weighted additivity. A lot has been made about sampling for PFAS in your wells. You need to check with your lab about the proper sampling protocols. You have to be very careful that you're not introducing part per trillion level contaminants into your sample. So you need to be sure that your bottles are not made of Teflon, because even though we don't worry about that necessarily as a human exposure route, it is a sample exposure route. So there are a lot of best practices for sampling materials. You want to avoid field filtering, because those glass filters will tend to absorb the PFAS and give you false low results. And then you want to use generally good sampling practices. The bottom line is, don't touch your sample. You know, wear a clean set of gloves every time you take a new sample. Do lots of QA/QC sampling to demonstrate that you have not introduced contaminants to your sample. We can provide clean water for people. Granular activated carbon, if you put enough of it on a treatment system, you will remove PFAS, despite what you might have heard in the media. This will work. You just have to scale it large enough. There are also ion exchange resins that are being used primarily in Australia that can remove them. And I'm going to get the hook very quickly here, I can tell. And then reverse osmosis. Looks like it works really good when we use it in the lab and if it's properly maintained, but we've seen some pretty mixed results on homeowner managed systems. But we do see very good reductions in people's blood levels when we treat their water and remove that as their primary exposure route. So this is the numbers we've seen in our exposed population following the addition of treatment to their water supply. There's lots of information about PFAS coming out from the ITRC. I've put this information in your slides. I won't talk about it too much, but we've got fact sheets. We're coming out with a longer document. We do in-person trainings. We're going to have online training, so I encourage you to take a look at the materials they've developed. Lots of people are working on this. The government's going to disavow any knowledge of what I've just said if they don't like it, so hold me accountable but not them, and I don't know if we have times for questions. But.
Well, so we're actually over, so
Sorry.
No, it's okay. It's important stuff. So thank you first. Are you here?